Good morning, everyone. Let us start this session. So in this session, we are going to perform the experiment number 3, which is the parallel force apparatus. So aim of the experiment is to verify the reactions of the simply supported beam using the parallel force apparatus. So in the equilibrium, that is module 2, we have studied the simply supported beam and how to find out the reaction of the simply supported beam by using the conditions of equilibrium. So simply supported beam, its schematic diagram is so this is the beam. So we can take this beam as a AB. So if this beam is supported at its two ends, so this is the reaction RA and this is reaction RB. Okay, so this is called as a simply supported beam. So if this beam is loaded by the point load, so here we have the point load W1 and this is the W2. Okay, so because of these two loads W1 and W2, the reactions will be developed at the support A and the support B. So by using the conditions of equilibrium, that is by using summation Fy is equal to 0 and summation of moment equal to 0, we can find out the reactions Ra and the reaction Rb. Okay, so this is the theoretical procedure to find out the reactions of the simply supported beam. So we have to verify these reactions by using the parallel force apparatus. So this is our experiment. So where do we see the simply supported beam in the real life? So this is one example. So the bridge is nothing but the simply supported beam. Okay, so here you can see. So these are two columns. These are used to support the bridge. Okay, and this is the beam. So on this beam, we can construct the concrete road. So this beam is supported at its two ends. So we can take this as A and this is the B. Okay. So these columns, they will provide the necessary support reaction so that it can support this complete beam or the weight of the beam. So if you draw the free body diagram for this complete beam, then you will show the reaction. This is the Ra. Okay. And here, this is the reaction Rb. And suppose some vehicle is passing over this bridge. Then it will provide the load. So we can consider this is W1 and this is W2. Okay. Here we are not considering the weight of this beam, but this beam, it will have its self weight. So we have to consider that self weight when we analyze this complete system. Okay. But this is the real life application for the simply supported beam. And this is your experimental apparatus. So here, this is the beam. So actually this is a wooden beam. Okay. And this wooden beam is supported at its two ends. This is A and B. Now we have to find out the reaction at its two ends, experimental. Okay. So we have connected the spring balance. So this spring balance, it will give the direct value of this reaction in kg or in gram. So right now there is no weight added on this beam. So the support reactions Ra and Rb both are 0. So we are neglecting the weight of the beam. Okay, due to self weight of the beam, the spring balance will show some value of the reaction, but we are neglecting that value and directly we are starting from the 0 value. Okay, so right now there is no weight added on the beam, so reactions are 0 at both its supports. Suppose we add the weight at different points on this beam. So these are two weights we have added at different locations with respect to point A. Now you can see the effect. Due to this weight added, you can see the change in the reaction. So initially it was 0 at both the supports. So Ra 0, Rb 0. When we add the weight, suddenly the reaction will change. So it becomes 0.2 kg and at the B it is 0.3 kg. So this is your experimental reaction. So spring balance, it will give the direct value of the reaction in terms of kg or in terms of gram. Okay. So right now in the animation, I have shown the digital spring balance. Okay. But during the experiment, we are using the analog spring balance. So we have to note down the reading from that spring balance. Now here, if I change the position of these two weights, so if I bring this weight close to the reaction A or the point A, then this reaction, it will increase compared to this value, and this reaction, it will decrease. So you can see this change. So if I connect the weight close to the reaction A or the support A, then you can see the change. So it has become 0.5 kg and this is 0.1 kg. Okay. So again observe. So initially both are 0. So here we have connected at some distance. So reactions was 0.2 and 0.3 kg. Okay. Now we have just shifted this weight close to the point A. So we get the reaction 0.5 kg and here 0.1 kg. So these are the experimental reactions. Now we have to verify these reactions by theoretical procedure. Okay. So for the theoretical procedure, we need to draw the free body diagram for this beam. So for the beam, we will draw the free body diagram. So we have already studied in the equilibrium how to draw the free body diagram. So we need to isolate the beam from its surrounding. Okay. So just I will remove that weight and I will show the weight as a point load. So these are the two forces. So this is W1 and this is W2. Then we will remove this spring balance. Okay. And we will show the reaction, which is Ra and Rb. So this is W1, this is W2, this is your point A, this is the point B, this is reaction Ra, and this is reaction Rb. Okay. What is unknown? Unknown is reaction Ra and reaction Rb. So we have to find out this reaction by using the conditions of equilibrium. For that, first, we have to observe the W1, sorry, it is distance with respect to point A. So I will assume this as x1 and W2 from the same point. So this is x2. Okay, so we will measure this during the experiment with respect to point A, or even you can measure this with respect to point B. So right now I have taken the distance x1 and x2 with respect to point A because I will take the moment about the point A. Okay. Now to find out these two reactions, we need to use two conditions of equilibrium. So using the conditions of equilibrium, so we have three conditions. One is summation fx0, summation fy0, and summation of moment 0. This condition we cannot use because the given system is a parallel force system and all the forces they are acting only in the y direction. Okay, so therefore we cannot use summation fx0. Now use summation fy0. So this is summation fy is equal to 0. Now for summation fy0, w1 w2 both are acting in negative y direction, so minus w1 minus w2, Ra and Rb acting in positive y direction, so plus Ra plus Rb, this is equal to 0. So from this you will get one equation as Ra plus Rb, this is equal to W1 plus W2. So take this equation 1. Use second condition, summation of moment 0. Summation moment, this is equal to 0. Now we have to decide the moment point. So take the moment point about which you can cancel any one unknown so that you can find out the remaining unknown. So you can select this point as a moment point, or you can select the point B as a moment point. So here I will take the point A, moment by all the forces about the point A is equal to 0. Now when we take A as a moment point, find the distance with respect to point A. So it is x1 and x2 for W1 and W2. Now write the moment equation. So moment equation, moment by the first reaction about the point A is 0 because Ra is passing through point A. Now moment by W1. So W1 is exactly perpendicular to this line. So this is the perpendicular distance, which is the x1. So moment will be W1 into x1, force into distance, and this moment it is a clockwise about the point A. So clockwise moment, it is negative. So this is minus W1 into x1. For W2, total perpendicular distance is x2 with respect to point A, that is a moment point. So moment will be W2 into x2, and this is also negative because it is a clockwise moment. Next is the reaction Rb into this total is the perpendicular distance. Okay, so we will assume this total distance as a length of the beam. So you can take this as a L. So Rb into L. And this moment, it is anti-clockwise. Okay, so therefore it is positive. So from this equation, you can write Rb, this is equal to W1 x1 plus W2 x2 upon L. So you will get the reaction Rb, and then put this value of reaction Rb in this equation and you can calculate the reaction Ra. So this is theoretical procedure to find out the Ra and Rb. These are the two support reactions, and we have to verify this value with the experimental value. So experimental value means the reading that we will get directly by observing the spring balance reading. Okay, so this is your complete procedure for the experiment. So actually that reaction R1 is not 9.5, it is 0.9 kg. Okay. Okay, so this was the experimental procedure to find out the reactions for simply supported beam. So you can repeat that experiment by changing the weight, and even you can change the position of W1 and W2 with respect to point A or point B, and you can repeat the experiment. Okay. So in the observation table, so first is serial number, then W1. So this will be in kg. Its distance with respect to point A. So you can take x1 and take this in meter. Then the load W2, its distance with respect to point A. So this is x2 meter. W2 is in kg. Then the reaction Ra. So this is your experimental reaction. And reaction RB. This is also experimental. By using condition of equilibrium, you will calculate the theoretical value. So Ra, theoretical value, and the RB. So this is experimental reading. And this is your theoretical value. So we have to verify this answer, Ra experimental, whether it is equal to or nearly equal to Ra theoretical. So for your first experiment, the W1, I have connected 1 kg. The position x1, so this was 26 centimeter, so it will become 26 10 to the power minus 2 meter. So it is 0.26. Then W2, it was again 1 kg. Its position was 71 centimeter, so it is 0.71 meter. The reaction that we got from the experiment, this is equal to 1.05 kg. So these reactions are also in kg. And the second reaction RB, it was 0.95 kg. Okay. Now let us verify this answer by using the conditions of equilibrium. So we will draw the free body diagram. Okay, so you can refer this setup. Okay, so it is similar to the physical setup. So here we have reaction Ra, and this value or this spring balance, it will give the value of reaction Rb from the experiment. So initially we have connected 1 kg weight. This distance, this is equal to 26. So it is 0.26 meter. And this distance, this is equal to 0.71 meter. That is 71 centimeter. Okay. So from this physical setup, you will draw the free body diagram. So your free body diagram will be like this. So you will show the point load, which is W1, 1 kg. This is W2, this is also 1 kg. Then here we have the support reaction, which is the Ra. And this is the support reaction, Rb. The distance is 0.26 and this is 0.71. Okay, so now use first condition, which is summation Fy, this is equal to 0. So for summation Fy, we will get the reaction as, equation Ra plus Rb minus W1, W2. So minus 1, this is equal to 0. So Ra plus Rb, this is equal to 2 kg. This is equation 1. Now use second condition, summation of moment by all the forces about the point A equal to 0. So take the moment by Ra, so that moment will be 0 about this point A. Moment by 1 kg, so this is equal to 1 into 0.26. This is negative. Again 1 into 0.71. This is also negative because it is clockwise. Then from Rb into. So total span. So it is 102 centimeter. Total length of the beam is 102 centimeter. So it is 0.102. Sorry, this is 1.02. 1.02 meter. So Rb into 1.02. And this is anti-clockwise. So this moment will be anti-clockwise. So it is positive. So from this, you will get the reaction Rb. This is equal to 1 into 0.26 plus 1 into 0.71 upon 1.02. So this is equal to so it is 0.95. So theoretical value for reaction Rb is 0.95 kg. Now put this value in this equation. So you will get the reaction Ra is equal to 2 minus 0.95. So it is 1.05 kg. So this is the reaction Ra, which is theoretical value. So you can take this theoretical value. From the experiment, we have got the value for reaction Ra. So this is equal to, so here this is 1.1 kg. That is a reaction Ra. And for the reaction Rb, this is 0.95 kg. Okay, so these are the experimental values. So in the observation table, experimental value, it was 1.1 kg, RB 0.95 kg, and theoretical value is 1.05, and this is 0.95. Okay. Similarly, for experiment number 2, that is reading 2, we have taken the same weight, 1 kg only, W1 and W2. Just we have changed the position. So X1, it is 33 centimeter. So it becomes 0.33 meter. Then position for the mass 2, this is 70.5. So it becomes 0.705. And array experimental value, so it is 0.9 kg. And RB value is 1.1 kg. So calculate these two values, theoretical value. Okay, we have to observe the same FBD. So when you solve for reading 2, then you have to draw the separate free body diagram. Then use conditions of equilibrium and then find out the theoretical value. Then for the third reading, weight is same, and this is 0.29 meter, that is 29 centimeter, and this is 78 centimeter. Experimental values are 0.96, and RB is 2 kg. Sorry, RB value, this is 1.04. And fourth reading, 1 kg weight, distance is 0.39 meter and 0.66 meter, and this is 0.98 and 1.02. Okay, so find out this theoretical value by referring the free body diagram. Okay, so complete this remaining 3 calculations. Okay, so this is your complete experiment to verify the reactions for simply supported beam using the parallel force apparatus.